turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists, the programme that brings you the latest breakthroughs in science, technology and medicine. I'm Chris Smith. And this week we're looking at the subject of batteries. With the global power supply shifting towards renewables, the battery is fast becoming one of the most vital forms of power storage. So how did we get here? How do batteries still need to improve? And could we all be flying in battery-powered airliners before too long? First, though, we inevitably need to understand what exactly a battery is. Now, in the year 1800, when the first battery was made, that's at least when it was documented, the person we would have asked then would have been the Italian chemist Alessandro Volta, and that's after whom, of course, we get the word volt. And what he did was to stack up a pile of copper and zinc plates, and he didn't know why, but he could show they produced a flow of electricity. Now, we don't have Volta to ask, but what we do have is the next best person. That's the formidable science communicator, demonstrator, and former naked scientist, Dave Ansell, who has turned up armed with lemons. You come bearing gifts.
I have come bearing many lemons.
What are you doing with them?
So I thought we could start off by recreating Volta's original experiment. I've got some copper, a copper nail, which you'd use to hold on a slate, and a zinc-covered nail, just a bog standard nail. And I have a lemon, and they're connected with wires to a voltmeter, which measures basically how hard the electricity is being pushed around the circuit. And if I put the copper nail and the zinc nail in...
Dave is just stuffing the two nails into the lemon. I'm not going to use that in a cocktail now. It's got zinc in it by the look of it. But they're close together, about a centimetre apart, the two nails, and they've got crocodile clips securing them to your voltmeter. And I now see on the voltmeter it's gone from reading 0 to 0.94.
volts, yeah, so nearly a volt.
So nearly a volt is coming out of that lemon.
So not quite as much as the battery you'd buy in the shops, but produces a current.
So why are we seeing a voltage when you stick those two metals? And what would happen if you stuck two of the same nail? Because I notice you have used a copper and a zinc nail like Volta did. Why has it got to be two different metals?
So we can try putting two of the same nails in.
Two zinc nails going in, and it says
Getting down to
there is no potential there.
Yeah. So what's going on is you've got two chemical reactions going on. In this case, on the zinc, there's a chemical reaction where the zinc atoms are losing electrons, and at the copper end, it's gaining electrons. It's probably actually the copper oxide is gaining electrons and turning back into copper. Those two reactions that can't happen on their own because you've got to lose electrons from the zinc and you've got to gain electrons on the copper. And so the only way they can carry on is by pushing electrons around the circuit and then back to the other side.
I see. So if the two were touching each other, physically touching, there wouldn't be a voltage documented on the multimeter because it would literally jump from one metal to the other. The zinc wants to give away those electrons and dissolve, and the copper wants to grab them and get rid of the copper oxide on its surface and turn into copper. And it's because they're separated.
Yes.
That's happening.
Because the only way that it can happen is by pushing electrons around. If they're touching, it's actually really bad. It's a big problem in boats and things. You've got two different metals touching each other. You get a battery and it will just you just flatten the battery and you'll oxidise your boat very quickly.
So what's the lemon for?
So all it is it's letting it balance out the charge. So you've got to push electrons around the circuit, but you also, if you're not careful, then one side will get very positive and the other side will get very negative. So the lemon, all it does is it allows charged ions, so charged atoms, to move around to balance out the charge. It doesn't actually have to be a lemon. I've got some salty paper down here, and you should find it does exactly the same thing.
You've got almost 0.9 volts on your multimeter.
Yeah.
So it's just the ability, once you make some zinc dissolve, you can get the dissolved zinc out of the way and more zinc can then dissolve. It's not getting crowded with trying to dissolve zinc. And the same going on at the copper. It enables that to happen.
Also, it isn't slowly getting more and more negative at the zinc side and more positive at the other side. Yeah, you've got to balance out the charge within the battery.
Otherwise no current could flow.
Yeah.
obviously we don't power out electrical devices with lemons with nails hanging out of them. So what's going on when we look at a compact cell, as we should strictly call it, that we put in, say, a phone or into a TV remote or something, what actually is going on in there? And why do you see different flavours of them? Some say alkaline batteries, some say zinc chloride. I mean, what's that all about?
So there's basically lots of different, if you use different metals, you get different voltages. So we can try, instead of using zinc, we can use basically some stainless steel, and that will produce a much, much lower voltage, now 0.15 volts.
Yeah, you've got virtually nothing with that.
So if you want to use different voltages, you can use different chemistries, and different chemistries can store different amounts of energy in the same space. Lithium-ion batteries, which are the big funky ones, work rather differently than this simple way. They're less of a chemical reaction. You've got a load of lithium ions, which would rather be in one material than another material, and so naturally, so they'll want to flow from one to the other, but you can push them back by charging it up. And then if you let a current flow, it'll flow back again. So it acts as a rechargeable battery.
So is the objective then to try to explore new combinations of metals or arrangements of the chemistry to try to get the right sort of compromise of what voltage you want and how much energy it can store?
Plus, there's also a load of really evil stuff going on, because there's not necessarily one reaction going on. There can be hundreds of other little side reactions going on, and quite often they can cause havoc in your battery. So actually what most of the research is going on is producing a battery which will last 1,000 cycles rather than just work twice and then give up the ghost because you made something else and it stops working.
Dave Ansell. You can find more from Dave online at sciansell.co.uk. So now we know what a battery is and how one works, how did a contained chemical reaction go from these rudimentary beginnings to one of the most important power sources in the world? Will Tingle spoke to historian and author of the book Charged, Jay Turner.
Lithium-ion batteries are actually probably one of the most recent battery chemistries that really have only been commercialized since the start of the 1990s. So, historically not that long at all. The very first batteries, the ones that became commercially available, that was happening in the late 19th century, and they were what we describe as zinc carbon batteries. Now they were single-use dry cell batteries that you would plug in, use, and then dispose of. So very different.
What is it about batteries that have allowed them to become so widespread, so completely integrated with our daily lives?
Often when we think about the story of energy in the 20th century, right, we think about fossil fuels and we think about coal and oil and gasoline and how transformative they were. But batteries played this little known but key role as in enabling technology and modern infrastructure, communication and transportation, because it's the ability to use a battery to turn the key of your car and start the car that makes it so easy to use that gasoline. Or batteries provide this portable power that can power portable electronics. And so they don't provide a whole lot of energy, but the fact that batteries provide a form of energy that's storable and instantly available makes them incredibly valuable. And so I think that's why they've become so important to kind of modern life as we know it.
I mean, we really cannot underplay just how important batteries are for all of us. It is a miracle of science that we can have a small cylinder that we can carry around in our pocket and just instigate power pretty much anywhere. And that power is pretty good for the size that the battery is. But is there anything to be said about the fact that lithium-ion batteries have been around for 30 years now and have ostensibly remained relatively unchanged compared to, say, the microchips and microprocessors that surround it in stuff like our phones?
Right. I mean, really interesting question, because one of the things that I find so fascinating is that batteries have improved, right? They've incrementally become better year after year. I mean, if you take the lithium-ion battery, just between 1995 and 2010, the energy capacity of a basic lithium-ion battery cell tripled during that time period. But during that same time period, right, the advances in microprocessor technology were an order of magnitude or more greater than that. And so, I think when you take a smartphone, there's so much more we can do with smartphones now than say we could 20 years ago, or maybe I should say a decade ago. But that's not just because the batteries have gotten better. That's been important, but the microprocessor advances mean that with that little finite amount of energy that we can get from the battery, there's a lot more work we can do just because of the computational efficiency. So I guess, the point that comes from me from this question is that it's not just about batteries, right? It's the advances in other technologies that batteries power that is just as important. So it's the efficiency of the microprocessors or the efficiency of the motors and the vehicles that batteries are being used in. That's important too.
Because we have this phone, this modern marvel in our pockets that can send signals into space and contact people a world away instantaneously. And the biggest complaint about it from the average user is that batteries die too quickly, or the battery life is getting shorter over time as it degrades. To the untrained non-chemist eye, which it was just to say mine, the battery, for all of its marvel, appears to be one of the weaker links in the technological chain. Is it a case of batteries being good, but because they contain relatively fewer components than all the other stuff that's innovating so quickly, there is a slight case of it being left behind?
You're exactly right. And, I describe batteries as just good enough. They're by no means perfect, but they're just good enough to enable electric vehicles or portable communication technologies or all of these other applications. And when I look at the history of batteries, it is largely a story of small incremental advances that have added up. And it's just tiny tweaks in the materials and the structure of the batteries that have made these differences. But when there are significant advances in battery chemistries, those have really fundamentally changed the way we use batteries in modern technology. And so, just looking back over history, right, you had those early zinc carbon batteries, and then the lead acid battery, which is the starter battery for most vehicles, that was, developed and kind of deployed at scale starting in the 1920s. And then in the 1950s and 1960s, you saw more advanced single-use batteries, alkaline manganese batteries. Those are the AA's that we think of today. And then in the 1990s, that was when lithium-ion batteries really began to emerge. And so lots of incremental advances, but then these moments when there have been new battery chemistries that have been put on the market that have become incredibly important to modern technology.
Speaking of modern technology, a lot of the focus around the future of batteries is going to have to be involved in integrating them into a renewable power grid. Are there issues surrounding batteries that will be sort of essential to overcome if we're going to make the best use we can of what we have in terms of renewable energy?
Batteries are going and are already playing an important role in enabling renewable energy transition, and that's only set to scale in the coming decade. And it must scale if we're going to move to a carbon-free economy. And I guess in my mind, kind of the big challenge is that scaling up batteries that quickly and at a scale to support that transition, on the one hand, means that we're going to be able to wean ourselves off of fossil fuels, which is incredibly important for all sorts of reasons, from public health to stabilizing the global climate. But zeroing out carbon means ramping up the use of a whole lot of other materials. So that means more nickel and manganese and graphite and, of course, lithium. And so at the same time that we phase out fossil fuels, thinking carefully about how we source these materials, how those supply chains get built, how we ensure that there's transparency and sustainability and that those materials can be reused at end of life. Those are challenges that are just as important as weaning ourselves off of fossil fuels in the first place.
Now that you know all of the history of batteries, where do you think the future lies?
Oh, I think more of the same. Lots of small incremental advances as we wait for that next battery chemistry that's a significant step forward that's going to displace the lithium-ion batteries that are so ubiquitous now.
Very thought-provoking. Historian and author there, Jay Turner.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound. Perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith, and this week we're looking at the subject of batteries. In a minute, could the future of air travel be battery-powered? Now, as Jay Turner alluded to earlier, it might appear that batteries are lagging behind the curve when it comes to technological innovation. But is this a fair assessment? And what could be done to improve batteries as we rely on them more and more? Well, with us to discuss this is the University of Warwick's Lewis Piper. Lewis, is it a fair assessment to say that batteries are a bit behind the curve?
Well, I would say that since about 1991, when the first lithium-ion batteries became available in portable camcorders, we've seen a 98% drop in the cost of production of these. They're a fraction of the price, that going from $5,000 per kilowatt hour production to $100 per kilowatt hour production today. And I think it's a case where it's that combination of being able to deliver all those applications that Jay mentioned in terms of portable electronics and electrification. And it's really a case where the abundance of manufacturing at scale has really played in. I mean, it's one where, for instance, with electrification, we've seen 50% of the electric vehicle in 2015 was essentially half the price was the battery pack. And that was why electric vehicles were so expensive. Now we're seeing in projections in 2023 where we're expecting a huge drop in battery pack prices such that electric vehicles become on par with petrol vehicles in terms of range and performance and cost.
And are those the main things that technologists, engineers, chemists are going for? What are the main targets? When people present a battery these days and they say, this is where we are, where are we aiming to be? What sorts of problems are we looking to solve in the next 5 years?
Well, I view batteries as a complex combination of chemistry problems and manufacturing problems. So we're always trying to balance 5 key components. We want to increase energy density, we want to increase power. So that means how much energy we can store and how fast we're using it. But we also have to balance that with cost. That's a critical component. Lifetime, we touched upon that. We want these to operate over decades. And the second component is safety. And so there's this complex equation where we need to make sure that the solutions we come up to improve energy density and power are ones which are compatible with manufacturing at the scales we need to provide ubiquitous power and energy for all of our applications, be them portable electronics to grid-scale solutions for renewable energy.
Indeed, and of course recyclability must play a part in that equation too, with an eye on being more sustainable in future, mustn't it? How are people approaching this then? Are they breaking it down into a sequence of problems that they're trying to solve one at a time, or are many people exploring different things in parallel? How are people trying to improve on batteries that we have today?
Yeah, that's a great question, because there's various roadmaps that exist in the industries for, especially like in the automobile sector, where it's that's a key area where different large companies are trying to vie for the solution. We talked about earlier that the battery is made up of active and inactive components, then you have to separate the chemical reactions. One of the key things with this is you can view your battery of having active components and inactive components. And to increase energy density, you want to increase how much active component you have as a proportion of your cell and your pack, which is the combination of your cells. And so there's things where engineers have been very effective at reducing the amount of packaging, the amount of inactive components you have, the cell design, and the cell to pack ratios, in order to give you those improvements, especially on the electric vehicle side. So there's one component with that. And then on the chemistry side, there's been the adoption of trying to move back to originally how we used to have in the first adoption of lithium intercalation batteries. They had lithium metal foils, which are very efficient. But the issue with that is safety and lifetime with those. And so a lot of the research activities like solid state batteries that people might have heard of, or new kinds of post lithium ion battery technology like lithium sulfur or lithium air, these are ones where there's a desire to return back to very thin lithium metal foils. And that's a very complex R&D problem that the industry is facing, how to get back to that and produce it at scale and cost that is competitive.
It's interesting though, because if Volta came forward 220 years and looked at a battery today, he would pretty much recognise what he had originally conceived of, though, wouldn't he, in the majority of batteries? Are we now in a point where we're also beginning to think outside the box a bit, or outside the battery box a bit, where we're coming up with batteries that he wouldn't recognise, whole new designs of how we do energy storage and transmission?
I think if Volta looked now, you're right, he would recognise there's two spatially separated chemical reactions that are facilitating the movement of charge and mass. But what I would say is he would recognise that what we're doing in terms of the periodic table is picking elements like lithium, which lithium and also the interest in hydrogen storage, these are our lightest elements that are able to easily release electrons. So it's hard to point to better elements. And what he'd also be surprised about is the massive scale of adoption we're doing in terms of how ubiquitous, how many of these we're making, how robust the manufacturing and the reliability of these cells are, and how we take them largely for granted, how well they operate.
It's been fascinating to talk to you, Lewis. Thank you very much indeed. That's Lewis Piper, who is at the University of Warwick. Well, suppose then that we heed all of Lewis's advice and we find ourselves in our hands a quick charging, high output, low degradation battery. Well, what avenues could, if we had that technology unlock? We've already got battery powered cars, we've got battery powered boats, but what about planes? Could we be charging off to a holiday destination sometime soon in a battery-powered airliner? Now, if you asked someone that a few years ago, they would think you were nuts, but that is actually the reality, and it's the thinking of a company called Cuberg. They are a battery company. They're based in California, and their founder is Richard Wang.
Ultimately, the purpose for electrification primarily is to mitigate carbon emissions that come out of these various segments of transportation. But when you look at aviation, it also goes beyond that. That might be the primary motivation, but electrification brings a host of other benefits, including much lower noise profile, much lower operating costs when fully deployed at scale because of lower fuel and maintenance costs. And ultimately, this lets you actually apply aviation into a much broader array of flight routes, flying much more flexibly to smaller airports, smaller towns, and ultimately allow people to move around much more efficiently and cost effectively as well.
It sounds great, but the problem is that batteries are big. And if you look at, say, the average electric car, it weighs twice as much as a petrol-powered car. So are you relying on improvements in battery technology to get you up in the air with this? Or do you think that with even present technology, you've still got an opportunity to do this?
Our focus is on developing more advanced next-generation forms of lithium batteries to enable electric aviation. You ultimately do need quite a few different things from your batteries. Weight is the nameplate metric that is most critical, and ultimately it's both energy per weight and power per weight. So how far can you fly, and can you get the energy out fast enough on takeoff and on landing, takeoff in particular for electric planes, to power your aircraft. And so you need a very special type of battery that does both a very, very high energy and very high power in a relatively small weight package. And so that is what we are really focused on delivering. Of course, in addition to this, you also need reasonable cycle life and charging times. And at the end of life, you need to be able to also recycle the battery effectively so that you have a fully sustainable solution. But ultimately, the weight of the battery and how much energy and power it delivers is the fundamental metric for success.
And when it comes to deploying this, how's it going to work? Are you basically going to have a slew of batteries in the bottom of a plane, and they're going to supply a whole heap of motors on planes? And will it work in a way that one would recognise as an aircraft right now with, say, 3 or 4 engines? Or are we going to fundamentally redesign how aircraft work because we won't have to deal with the constraints of present jet engine technology, which has, to a certain extent, dictated how we build aeroplanes hitherto?
There are many, many different types of electric aircraft designs currently in development. And the reason for this is that this sort of natural selection and evolutionary process has not fully run its course yet. Typically, these are not what you would think of as jet engine aircraft. They would be more reminiscent of propeller-driven aircraft. And the difference is, yes, you have batteries, and yes, you have electric motors driving propellers, but because you don't have a standard powertrain, you have cables carrying power, it's actually much more flexible to put a lot more propellers if you need to, wherever you want, all around the aircraft. This lets you build aircraft that are much quieter, potentially, much more energy efficient. And it also lets you build aircraft that are not only, let's say, standard small electric planes, but also some of these more unique concepts that are vertical takeoff and landing. So think of a helicopter, but with many more propellers designed for urban air mobility, and that flies much more efficiently with much less noise compared to a helicopter.
One of the other big constraints with the technology we have at the moment with cars is how long it takes to charge them up. And many air operators, people who are doing fast turnaround passenger trips, are turning their planes around in very short times. Can we recharge an electric plane in time, or have you got another solution to that problem?
When you look at charging infrastructure, typically the two solutions are either to charge the battery in the aircraft or to try to swap the battery at the end of a flight. So far, what we've seen in the industry is most companies are preferring to charge their aircraft rather than swap, because swapping introduces a host of technical and regulatory challenges. And so charging time, it turns out that it's not as critical as in automotive, where you're on a road trip and you're just sitting in the car waiting for it to charge fully before going again. In a typical electric aircraft business model, typically you fly to your end destination, you get off the aircraft, and then while the aircraft is on the ground, you plug it in. You actually have to clean the aircraft, you have to load passengers, load and unload cargo, do check-ins and so forth. And so given how these aircraft are operated, fast charging is still important, but not as critical as in the automotive industry.
Over what sort of timescale are you hoping to do this?
We believe that many of these industries will electrify by the end of this decade, although to varying extents. In aviation, we see a dramatic transformation of the aviation industry, particularly for smaller electric and hybrid electric aircraft flying up to a few hundred miles of range, where by 2030, we will see likely the majority of these aircraft becoming fully or partially electrified.
And the environmental impact, will this be better?
It will be dramatically better for two key reasons. One is that electric motors are much more efficient in terms of energy use compared to combustion, roughly 2 to 3 times more efficient. So you're just using less energy when you're converting that into propulsion. And then in addition, of course, by using electricity, assuming you have a reasonably clean power generation grid, then you can also greatly mitigate the carbon content of the energy that's used for the flight itself. And so we're looking at very dramatic reductions in carbon content, similar to what EVs are doing compared to existing combustion vehicles.
And finally, one of the most important considerations is how fast you go, both for the convenience of passengers, but also the faster you go, the more drag there is, and therefore the more fuel you burn at the moment with our present technology. So will we be looking at speeds and journey times with this technology, electrification, as equivalent to what we have at the moment with fossil fuels?
These kinds of electric aircraft will not be competitive with jet engine powered aircraft from a speed or from a range perspective. That will be other kinds of technologies like synthetic fuels and hydrogen to power future cleaner jet aircraft. If you look at battery aircraft, they will be propeller driven, but with that being said, they will be likely comparable from a speed perspective with existing propeller aircraft. The benefit is that with electric aircraft, though, they're much more flexible. And so rather than going into a very, very big international airport to fly where you want to go, even if you're not going very far, you can get into a small local airport with much more efficient check-in times and security lines and everything else. And that, I think, practically has a much higher benefit in terms of time savings compared to the aircraft itself.
Always good to end on some ambitious forward thinking. Richard Wang there. And that's it for this week. Next week, we'll be taking a closer look at human memory and why the University of Cambridge wants to find people who have superhuman powers of recall. How do memory masters do it? If you can remember, tune in next time and all will be revealed. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.